This is 3.5, graphs of linear inequalities. So our two objectives are going to be verifying solutions of linear inequalities and then sketching graphs of linear inequalities. So we have inequalities, right? We have the less than, the greater than, less than or equal to, and greater than or equal to symbols. And an inequality like x is greater than 5. We've talked it before, you've done it before in Algebra 1, or you'd graph that on a number line, right? This stands for numbers greater than 5. So you do your little number line, and maybe this is 5 right here. 2, 3, 4, yep, that's 5. So then you had to decide, well, open or close circle, in which way my arrow is going. So because it's a greater than 5, and the numbers that are greater than 5 are these numbers over here, right? Like numbers like 6, 7, 8, 9, 10, infinity. And then numbers like 5.001, that's still greater than 5. But 5 isn't greater than itself, right? 5 is not greater than 5. But 5.001 is greater than 5. So we want an open circle here to show that 5 is not a solution, but everything that's right up next to it is, and anything bigger is going to be a solution. So those are inequalities, right? And to give you another example, x is less than or equal to 1. So you'd find the point 1 and you'd say, okay, what numbers are less than or equal to 1? That'd be those numbers down this way, right? Like -10, -20, 0. And then you decide, well, is 1 less than or equal to 1? Yeah, it is. It meets that or equal to part. So it can be the point 1. So instead of an open circle, we'd have a closed circle, right? 1 can be a solution to this. 1 and anything below it. So those are inequalities, and those are graphing inequalities. But now we're going to be doing linear inequalities, which means line. Okay, just like we graphed the line y equals 3x plus 2. Well, this is our y-intercept, and this is our slope. So we'd go to positive 2 on the y-axis, and then our slope is 3 over 1. So you'd go up 3 and right 1, and then you connect these dots, and you have a line. So we're going to be doing something like that, except now instead of an equal sign, we're going to have one of our inequality signs, less than, greater than, less than or equal to, greater than or equal to. And that's going to change our graph a little bit. Okay, so more specifically, a linear inequality in two variables, x and y, is an inequality that can be written in one of the following forms. A and B and C are just numbers. So we could have 3x plus 2y is less than 7. Negative x plus 10y is less than or equal to -1. And so on and so forth. And you could have these different forms. Basically, the only thing that's changing is their inequality symbol. Okay, so those are linear inequalities in two variables. So an ordered pair x, y, an ordered pair, that's the key part there, not just a number. An ordered pair is a solution of a linear inequality if the inequality is held true, right? So last section we decided, hey, is the point 1 comma 2 a solution for this line? And so you would plug in 1 for x and you'd plug in 2 for y, and you'd see if both sides were equal. So 3 plus 2, that side's 5 and this side is 2. No, it's not a solution. Okay, so if I have an inequality like this and I say, is 1 comma 2 a solution, you'd plug in 1 for x and 2 for y and see if it really is less than 7. If it's less than 7, we call it a solution. So let's practice that. Determine whether each ordered pair is a solution. of the inequality 2x minus 3y is less than negative 2. So I have my x and my y, and I want to plug those in. So 2 times x minus 3 times y. Is that a number? Does that give me a number that's less than negative 2? Well, this would be 0 minus 0. So is 0 less than negative 2? And if you're unsure, think about your number line. Think about if this is 0, 1, 2, and then you have negative 2 over here. No, 0 is bigger. It's further to the right. So this is false, right? It's not true. So this would not be a solution. Go ahead and see for me, is 0, 1 a solution? Okay, if we would have got a number here like negative 10, is negative 10 less than negative 2? Yep, it sure is. It's going to be a solution. So I want you to plug this in. If it's a true inequality, it is a solution. If it's a false inequality, it's not a solution. Okay, when you plugged in 0 for x and 1 for y, you'd simplify this side to get negative 3. And you're checking to see, is negative 3 less than negative 2? So if you don't know right off the bat, make a visual, make a number line, and see if this is negative 2, negative 3 is behind it, so negative 3 is smaller. So this is a true inequality, so this would be a solution. Now determine whether each ordered pair here is a solution. Okay, so we're going to do the same thing. I'll do one, and then I'll have you do another. I'm going to do this one. I'm going to do B. So it's negative 3 times x, so I'm plugging in 3, plus 5 times y, plugging in 3, and checking to see, is it actually greater than or equal to 6? So negative 3 times a positive 3 would be a negative 9, and 5 times 3 would be 15. I'm putting a question mark above the symbol because I don't actually know if it's greater than or equal to. Negative 9 plus 15 would be a positive 6. Is positive 6 greater than or equal to 6? Yes, it is. It's not greater than, but it's the or equal to part, right? They're equal. So this, because this is true, this would be a solution. Go ahead and solve A for me. Determine whether negative 10, negative 3 is a solution. Okay, when you plug in negative 10 for x and negative 3 for y, this side would simplify to a positive 15. Make sure you're watching your signs. A negative times a negative would be a positive 30. Positive times a negative would be a negative 15. And a positive 30 and negative 10 make positive 15. So positive 15 is greater than or equal to 6. That's true, so it is a solution. Okay, sketching the graph of a linear inequality in two variables. All right, so we think of it like if it were an equal sign and we graph it that way. Okay, typically we like to put it in slope-intercept form. That's the easiest form to graph. Okay. The only thing that we need to be cautious of, actually there's two things we need to be cautious of. One of them is the line. We could either have a solid line or a dashed line. A dashed line is used when we have the less than or the greater than symbols. A solid line is when we have our or equal to symbol. So you can think about it this way. Solid line is that or equal to line underneath. If you see that line underneath, think it's a solid line. Okay, if there's no line underneath, you're thinking it's a dashed line. Okay, so that's one thing we need to be worried about. The other thing that we need to be worried about is shading. The reason why we shade in these graphs is because a linear inequality is a collection of all solution points. Okay, right? Just like in my opening example on our inequality, we had an arrow pointing to the right on the red and an arrow pointing to the left on the green. Those were shading you to show you there's more than one number that's greater than 5. There's a lot of numbers greater than 5, and they're all over here off to the right. So I'm going to shade in that direction. because 6 is a solution, 7 is a solution, 8, 9, 10. That's a lot of solutions. That's an infinite amount. So same thing with a linear inequality. We're going to have a lot of solution points, so we need to shade. Okay, here's what I'm talking about. This is a linear inequality. X is greater than or equal to -3. Now, I want to graph it. Okay, and typically we like to put things in slope-intercept form. But this doesn't have a y, does it? So it's a special type of graph, if you remember. If I replace the inequality symbol with an equal sign, this would say x equals -3. This is a vertical line, right? It crosses the x-axis at -3. So find the x-axis, find -3, and put a point. Okay, it's going to be a vertical line. However, remember I said I need to be careful for a dashed line or a solid line. So look at that symbol. It has a line underneath it. That means solid line. So I want a vertical solid line to represent this inequality. Okay, so nothing's changed so far except I had to be careful about the dotted versus solid line. And then the next thing I need to be careful about is the shading. Okay, so what we're going to do is test points. I always like to test the point 0, 0, but we could test any point that's not on this line. That's the important part. You don't want to test a point on the line because we already know every number on this line is a solution. Okay, so I'm going to test 0, 0 if I can. That's this point over here at the origin. And the reason I test 0, 0 is because it's easy to plug in. 0 is the easiest number to work with. I could test 1, 1 if I wanted. I could test -6, -7 if I wanted. But 0, 0 is simpler math. So what I do when I test is I'm plugging in 0 for x and 0 for y. Well, there's only an x here. And same thing, I'm checking to see, is 0, 0 a solution point, just like we did in these last examples? Is it a solution? So when I plug it in, is 0 bigger than -3? Well, think about your number line again. -3 is smaller. Okay, 0 is bigger. So yes, this is a solution because that's true. So because 0, 0 is a solution, and because a linear inequality shows all the solution points, I need to make sure I shade in the region where that point was. Right? If the point satisfies the inequality, that means if it's a solution, shade the side or the half plane, I say side, of that region that satisfies the inequality. So 0, 0 was a point. I need to include 0, 0 as part of this solution. Right? Just like here, if I plugged in 6, 6 is greater than 5, I want to show that I'm shading to the side where 6 is. Right? I'm not shading to the side of 4 because 4 is not greater than 5. If I wanted to get fancy, which I don't need to, and you don't have to write this in your notes, but you can always test another point and maybe one that's on the opposite side. So one that'd be over here would be the point on this side, let's -4, 0. And let's see what happens when I test this point. I plug in -4 for x and decide if it's greater than or equal to -3. And no, it's not. It's smaller, right? So it's not a solution, which means I don't want to include it on my shading, right? So I shaded correctly the first time. I'm shading to the right side of this line. And if I were to extend this line up like it should go all the way, any number over here and all the way back to infinity, like I could keep extending this, right? As long as it didn't cross that line, it's a solution. right? Any ordered pair over here that I pick and test, it's going to come out true. Also on the line, they're going to be true, right? Let's pick a number on the line, like this one right here. That's -3, +1. If I plug in -3 for x and I test, is it greater than or equal to -3? Yes, it is. It's a solution point, right? It's part of that line. So think of this as a closed circle, right? So we had open circle and closed circle. This one's a closed circle, which also means a solid line. Let's look at one that wouldn't be a solid line, right? I have y is less than 4. If I think about this as an equal sign, y is equal to 4, I know that's a horizontal line. It crosses the y-axis at 4. So it's going to be horizontal, but I want to think, before I draw this horizontal line, is it going to be solid or dotted? And it's going to be dotted because of that less than symbol. It's not or equal to. Right? So this line, I'm going to dash. The reason I'm dashing it is because if I were to test a point on this line, which we'll do later, if I were to test a point on that line, it would not satisfy that inequality. Okay, we'll get to that later, but first let's test a point not on the line. So pick a side, either the top or the bottom, and test that point. Again, if I can, I test 0, 0. So I'm checking to see, is 0, 0 a solution? So plug in 0 for x, but there is no x, so I'm plugging it in for y and seeing, is it less than 4? Yes, that's true. So it is a solution. Because it is a solution, I want to shade to this side of the line. All of these numbers beneath the line are solution points. Now let's get back to what I was saying about on the line. This point right here is on that dotted line. Let's test it. Let's see if it is a solution. I know everything under the line is, because I tested 0, 0, and 0, 0 was under the line. Let's test the point 1, 4. Plug in 1 for x, it's not there. Plug in 4 for y. Is 4 less than 4? No, it's not. It's equal to, but it's not less than. They're the same amount. Okay, so this would not be a solution. Therefore, I don't want a solid line going through that point. A solid line represents any point on the line as a solution. But a dashed line represents, hey, each one of these won't work. They won't work. It's just going to be false when I plug them in. Okay, so that's the reason for the dotted line. And it's going to be that way anytime you have a less than symbol. If you wanted to get fancy, you could test a point above the line, see if you did it correctly. Remember, you only have to really test one. If you test one and do it correctly, you get the right answer. I'm testing 3 just to show you why it's working or what's not working. So that's the point 0, 5. Okay, so I plug in 5 for y. Is 5 less than 4? Again, no. It's not a solution. I don't want to include that as part of my solution. I don't want to shade up top. But I do want to shade below. Okay, so those were the special cases, right? The horizontal line and the vertical line. Let's look at more of the common lines, such as y or x plus y is greater than 3. So first thing we need to do is either 1, put it in slope intercept form. That's one way to graph it. Another way to graph it is to find the intercepts, x and y, and graph those. Another way to graph is to fill in one of those t-charts, right? and you decide, you figure out what y is. For this method, I think I'm going to use intercepts. Okay, so let's find the x and y intercepts. Remember to find the y-intercept, we're going to let x equal 0. So let's start with y-intercept. I'm going to plug in 0 for x and solve for y. So 0 plus y would just be y is greater than 3. And for the x-intercept, I'm going to plug in 0 for y. Use green again. Okay, so those are where it's crossing the x and y axis, right? They're intercepts. So at the point 3, it crosses the y-axis. And at the point 3, it crosses the x-axis. Those are my intercepts. So I graphed them. Now, how do we want to connect them? A solid line or a dotted line? Well, here it's going to be dotted, right? And the reason I know that is because of the inequality symbol. If it were solid, it would have a solid line underneath it. Okay, so I'm going to connect them. And next I need to test a point, right? So I made sure if solid or dotted. Next I need to test a point in order for me to shade. So because 0, 0 isn't on the line, I'm going to test the point 0, 0. So when I plug in 0 for x, I plug in 0 for y, I'm checking to see, is this side 0 greater than 3? And no, it's not a solution, is it? 0 is not greater than 3. Okay, so what happens when it's not a solution? Don't want to shade that side. I want to shade on the opposite side, where 0, 0 isn't. So all these numbers over here are solutions. Okay, so when I test it and I get not a solution, do not shade to that side because it doesn't satisfy it. Remember, the shaded region is all of the points that do satisfy this inequality. They're all the points that when I plug in x and y, they're going to be bigger than 3. Okay, let's look at this example. 3x minus y is greater than or equal to positive 2. So again, I have my 3 different ways that I could potentially graph, right, from the stuff that we learned in part 1 test. You'll put it in slope-intercept form. You could find the intercepts. You can make a t-chart. This one I think I'm going to put in slope-intercept form, just so you can see 2 different methods. All right, so let me move this down. We're over. If I were to solve in slope-intercept form, I need to get y by itself. So I need to move this whole 3x term, not just the 3 and not just the x. I want to move both of them. It's positive, so I'm going to subtract it on both sides of my inequality. That way those add up to 0. And I'm left with negative y. Drop down my greater than or equal to symbol. I have a negative 3x and a positive 2. These aren't like terms. I can't combine them to be negative 1x. Okay, so it's negative y, which means that's a negative 1y. Since y is being multiplied by negative 1, I'm going to divide by negative 1. If I do it to one side, I have to do it to the other. So those negative 1s will 1 out. They'll cancel. And I'm going to change the sign of negative divided by negative, so that would be a positive 3x. And a positive divided by negative would be a negative 2. Now there's one thing I want you to make sure of. when you're working with inequalities. Multiplying or dividing by a negative number on both sides, we need to flip that symbol. Remember, we talked about this in chapter 1. I divided by a negative number. I'm going to flip the direction of my arrow, of my inequality symbol. Okay, it's in slope-intercept form, so now I'm ready to graph it. So let's first plot our y-intercept at -2 on the y-axis. And then we have a slope of 3, which means 3 over 1, which means I'm rising 3 from this point, 1, 2, 3, and I'm running positive 1, and I'm putting another point. Okay, how do I connect them? With this symbol here, this is a solid line underneath, so I'm going to graph them with a solid line. I'm going to connect them not with a dotted line, but with a solid line. Whoops, I just realized I didn't do that here. I wrote dotted, but I did a solid line. So something you got to be careful of every time. Even I still mess up on it. This should be dashed. Otherwise, you're going to get the wrong answer. Right? The reason it's dashed or dotted, some people say dotted, some people say dashed, is because of this symbol. It doesn't have a solid line under it. So I apologize there. This one is solid for sure. Okay, so solid line because of my symbol, or equal to, which means any point on this line is going to be a solution, right? If I kept going up 3 and over 1, oh, that point right there, 2 comma 4, that's going to be a solution if I tested it, right? So let's test a point and see what other solutions do we have. Like, should I be shading all of the points over on the left, or should I be shading all the points on the right of it? So let's go ahead and test. Again, I can do 0, 0 since it's off of the line. So it would be 3 times 0 minus 0. Is that greater than or equal to positive 2? And again, I'm testing the original. Okay, I could test this one also, and if I did it correctly, it would work. But if I messed up on the algebra somewhere, I'd get my shading wrong, right? Or if I forgot to flip the inequality symbol, I'd get it wrong. So it's your best bet to plug it back into the original. So 3 times 0 is 0, minus 0, that'd be 0. Is 0 greater than or equal to positive 2? No, right? This is not a solution. So what happens when 0, 0 is not a solution, or the point that you test is not a solution? You don't want to shade to that side, right? You want to shade to the opposite side. So don't include 0, 0 because it doesn't fit in your inequality, which means all of these points over here will fit. Okay, so shade how you want. Some people get real dark. On your WebAssign, you'll see what it looks like. It kind of looks more like this. It does a more accurate picture of shading it. Okay, if you have any questions, please don't hesitate to ask. You really need to be good at graphing lines. Graphing lines from that part 1 test, you need to be good at for you to be successful in the rest of this chapter. So please come get help if you need it.